Okay, so this mini lesson is about what are referred to as standard angles on an XY plane, so on a set of axes. And up until this point, the majority of your trigonometry has been related to triangles, and so angles within triangles. And so we want to expand your horizons a little bit and start investigating angles that aren't necessarily contained within a 90-degree angle and can be drawn on an XY set of axes. Okay, so we got to get some terminology down. So first of all, angles are typically, and we got to get the language, I haven't spoken about it yet, but an angle is basically defined as having two arms which are rays. Okay, so I'm going to make one line here, put a little arrow on it, and that's a ray. So it starts at a point and it goes off to infinity by the arrow. And then for an angle, that is called what is referred to as the initial arm. And then an angle is formed when, imagine, and I'll do it in a different color, and I'm going to erase this in just a sec, but imagine if I drew a blue one right over top of that one, and they were right on top of each other, and they're basically sharing the same line. There is no angle. The angle is 0 degrees in between them. But imagine if I took the blue one and started to rotate that blue one. Okay, and so if I rotated the blue one, it would the whole thing would open up, right? And so that opening up right there, as the blue one swung open, that forms an angle, and that angle we typically call that theta. But the blue one is what's referred to as the terminal arm. And so an angle is formed between an initial arm and a terminal arm, and those two rays share a common vertex. Okay, so just kind of some basic fundamental terminology there. Now, standard angles, when we're talking about trigonometry in terms of a coordinate plane, a standard angle takes what I just drew, that last diagram, and it takes that and whoops, let me redraw that. Why won't it straighten? There we go. Okay, so if we take that last angle and I draw the vertex smack dab on the origin of an XY axis. Okay, so I'm going to make my pen a little bit thicker here so that we can see this a little bit better. So there goes the initial arm. And there goes, oops. Okay, so the initial arm is right there, and the terminal arm is right there, and the angle in between them is theta. So anytime you have an angle where the vertex is actually at the origin of a coordinate system, and the initial arm is on the positive x-axis. Okay, so that's where the big thick black one was there, right there. And then the terminal arm swings open from there. The angle that forms is called a standard angle. Okay, so this guy, what I've just drawn, is referred to as being a standard angle, and it would be any angle, and it doesn't matter what size the angle is, but it's any angle where the vertex is at the origin and the initial arm is on the positive x axis. Now, having said that, any angle, like an angle in a triangle, you could draw a triangle on this set of axes. So I could draw, if I had my set of axes like this, and I drew a triangle right there, like a right angle triangle, well, that theta right there, that angle of that triangle would be considered a standard angle. Okay, which is, that's an important one to note for later on as we progress through this, because we're going to need to start drawing triangles on our xy axis. Okay, so a standard angle, if you can kind of see this, I'm going to erase my triangle right here. But I'm going to keep this set of axes. Actually, I think I'll redraw it just to make it bigger. So again, if here is my x and y axis, then there's actually, hopefully you can see this, there are 4 parts to this, and I'll put them in 4 different colors. Okay, so the first one I'll do in yellow. So this quadrant, this section over here, right in between, that's bound between the x and the y. Okay, so all of this region, so I didn't draw it right up close. Okay, all of that section right there, that is referred to as quadrant. Whoa, how do you spell quadrant? Quadrant 1. This section over here, as you go counterclockwise, that quarter right there is called quadrant 2, and then so on and so on and so forth. You probably figure out where I'm going with this. This is quadrant 3. And obviously quadrant 4. So it starts in the typical positive, positive, positive y and positive x is quadrant number 1, and then it goes counterclockwise from there. And the 4 quadrants are important because you can have standard angles where, so the initial arm will always be in the same spot. Okay, so the initial arm is always going to be on the positive x axis. Okay, so any angle, again, I'm going to make it a little bit thicker here. So the initial arm is always going to be on the positive x-axis. Now, what changes is where the terminal arm can be. So if the terminal arm happens to be here, then this angle is in quadrant number 1. But the terminal arm could be over here too, right? And so now that's a bigger angle, right? So theta is there, and that angle is not going to be contained within a 90-degree triangle, right? So the one that I've labeled there as theta in red, that can't be inside of a 90-degree angle. It's too big. But that would be an angle where its terminal arm is in quadrant number 2. And then you can have, obviously, it can keep going. Now, it's important that you understand, or that you see, that I keep turning in a counterclockwise direction. So the direction that I'm making the arrow there. So to be in quadrant number 3, you have to go past 2 axes to get into that third quadrant. And so it's actually almost rotating the entire way. And then obviously the last one would be to have your terminal arm there. And I know it's like your mind's eye kind of wants to see the acute narrow angle there. But if we're talking about a standard angle, then we're talking about that angle there. Now, in your own mind, you probably already know this, that if that red theta that I drew right there, if I kept swinging the terminal arm, okay, so the terminal arm being, let's make sure that we have this labeled so you know what I'm talking about. So that's the terminal arm. So imagine that if you kind of wind it back clockwise over to where it started, think of the initial arm as being kind of embedded on the x-axis, like it's stuck there, cemented down. And then the terminal arm can swing like the arm of a clock, but it goes counterclockwise. It goes the opposite direction. So as it opens up and opens up and opens up. And when it gets straight up and down, that would be at a 90-degree angle. So this right here is 90 degrees. If it kept swinging and it got over to the negative x-axis, this would be 180 degrees. And then if it kept swinging and got 3/4 of the way around, it would get to 270 degrees. And then if I kept swinging it until it got back to the x-axis, okay, which is, I mean, it's kind of a weird thing to be thinking about. So I have to erase this because I can't go backwards because I'll take all the numbers off there. Okay, so imagine if I took the arm and swung it all the way around until it got back to the very beginning again. So I think I originally did the terminal one in blue. So imagine if I did the blue one right over top of the black one again. Then that would have gone around 360 degrees, right? It would have done a full circle. And so if you go all the way around, like if the arm of the clock spins all the way around one full rotation, it's gone 360 degrees. So knowing that, like how many degrees it is to go from one section to the axis, from one axis to the next axis is an important concept to know. We are going to, just for this little bit right here, we are going to focus on quadrant number 1. Okay, so angles that are in quadrant number 1. So I just want to show you this one little brief thing. And if I were to hold on for just a second here. So okay, so I'm going to take okay, so you've got your X and your Y. And I'm going to label a point on here. Okay, so I'm going to say what are the values And okay, so what are the trig values and magnitude of the angle that has a terminal arm passing through, we'll go 4 comma, we'll go 4 comma 6. Okay. So I've asked that question, okay, and it's actually a multi-part question. But first thing I want to do is I want to make sure that you can see what I'm talking about here. So it says you have to know your terminology. So it has a terminal arm passing through 4, 6. Well, the assumption in that question is that you know the initial arm is there. Okay, so the initial arm, and let me just label it. Whoa, bad arrow. Because it's always there. It's always on the x-axis. The terminal arm is going to be through the point 4, 6. Okay, so where is 4, 6? So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So there's the point 4, 6. Okay, so the x is 4 and the y is 6. And so it has a terminal arm going through that point. Okay, so the terminal arm goes through there. And so the description, because it gives you a point and it says that it has a terminal arm that goes through there. Well, obviously the terminal arm starts at the origin of the xy axes, and then passes through that point. And so because you've got 2 points, you can draw the line. And because now you can draw that, you've drawn that line, now you can say, well, the angle that we're talking about is that angle right there. And I'll label it as theta. So that's the angle that we're talking about. And so first thing you have to be able to do is actually be able to draw it. Okay, now obviously we're going to work more on quadrant 2, 3, and 4 later on. But we're just working on quadrant 1 right here. When you draw this, you need to be able to see, and this is where practicing with the triangles was important right at the very beginning, because you need to be able to see a triangle that's on here. And the triangle has to do with the point that we originally drew. So that 4, 6. So that 4, 6 right there actually forms a right triangle. And I'm going to highlight it here. It forms this triangle, right? So it forms that triangle. And because you know the point, you know the sides. And because it's like on a coordinate axis, we know that that's a 90-degree angle. Right? So it actually, every angle that you draw in standard form on an XY coordinate plane can be drawn as a right angled triangle. Because the x and the y coordinates, they're perpendicular to each other, right? And they're perpendicular to the axes as well. So everything's all at 90 degrees when you do that. So you've got a triangle, and you know what the lengths of the sides are. That length is 4 and that length is 6. And so because you know the lengths of those two sides, and you're talking about theta being that angle there, well, the 6 is the opposite, the 4 is the adjacent, and so right now you could do the tangent of it, no problem, right? However, what is the hypotenuse? Okay, so the hypotenuse would be this distance right here, right? So that would be the hypotenuse. Not the entire, like not beyond that point, just from the origin to that point. Okay, so from 0, 0 up to that point. Well, how far is that? Well, we would use Pythagoras for that. Seems to be the easiest thing to do. And we're not going to use the calculator to round this off. We're going to leave it as a radical. If it ends up being a radical, we're going to leave it as a radical. So we'll put in 4 squared plus 6 squared equals c squared. So you've got 16 plus 36 equals c squared. So you've got 52 equals c squared, and you've got c equals square root of 52, which is divisible by 4. So c equals 2 root 13. Okay, so the hypotenuse there, well, it's kind of a weird one, but the hypotenuse, let me get rid of this actually. So that side right there is going to be 2 root 13, and that's the hypotenuse. So just by knowing a point and knowing that you're talking about a standard angle and what that means in terms of the initial arms and where the terminal arm is, and it has to go through that point, you can then draw it. You can draw a triangle, and because we've gone through SOHCAHTOA and we know enough about right angle triangles and trigonometry that now we can take these numbers and actually go ahead and answer the rest of the question. So the sine of theta would be the opposite over the hypotenuse, which would be 6 over 2 root 13. Which, whoops, let me simplify first, because actually simplifying first is easier. So the 2 and the 6 cancel to give me 3 over root 13, but we rationalize. So 3 root 13 over 13, that's the sine. The cosine is adjacent over the hypotenuse, which would be 4 over 2 root 13. Again, that simplifies to 2 over root 13. The 4 and the 2 cancel. And then rationalize. And this is why we had to rationalize earlier in the course. Whoops, how did that change to a 3? Oopsies. Okay, so it's 2 root 13 over 13. And then tangent is opposite over adjacent. So that is 6 over 4, which simply reduces to 3 over 2. And I'm going to leave it as a fraction. Okay, so it does equal 1.5 if you want. Okay, so those are the 3 trig values. So the sine is 3 root 13 over 13, cosine is 2 root 13 over 13, tangent's 3 over 2. If I want to know what theta is, I would choose the easiest one, and I think the easiest one on there is tangent. So tangent theta equals 3 over 2. Theta is going to be, and this is what I was showing you in the online class, you take the inverse on your calculator. You do that. And so that would be, you're going to punch in either 3 over 2 on your calculator or 1.5. And let me quickly go to my calculator. Whoa. So I'm going to go second function, tangent, 1.5. Oops. I think this 1.5 second tangent. Yeah, there it is. 56.3. Okay, so 56.3 degrees. Now, if you don't trust yourself, you can figure out. You'd have to change it to a decimal, but you could punch into your calculator 3 root 13 divided by 13 gives you some decimal that's less than 1. You inverse sine that, and it will hopefully give you 56.3 as well. And you do it with cosine as well. They'll all give you 56.3. So it doesn't matter which one. So, whoops. So right there, it does not matter which function you choose to figure out the angle. I mean, the angle's the same for all of them, right? So it's just a different function. So back in here, that red theta is actually 56.3 degrees, which kind of looks like 56.3 degrees actually. Certainly looks more than 45 degrees. And so that's how you can take a point on a graph that just has an x and a y, and you can convert it. You can figure out what the trig values are and what the angle is by inversing that function. Okay, that's it.